Every Caterpillar tractor that rolled off the assembly line in East Peoria, Illinois in the 1930s and 40s was loaded onto a rail car and shipped down the road. Not to a dealer, not to a job site, to another factory, R.G. LeTourneau's factory. Because without LeTourneau's cable control unit bolted to the back, a Caterpillar tractor could not cut dirt, could not push earth, and could not pull a scraper. It was just an engine on tracks. More than 60% of all Caterpillar crawlers built during that era left LeTourneau's plant, not Caterpillar's. And when Caterpillar finally tried to cut LeTourneau out during World War II and build their own attachments, the United States War Production Board stepped in and told them to stop. The government ordered Caterpillar to keep buying from LeTourneau because switching suppliers in the middle of a war would have crippled Allied construction across 2 continents. That is how much power one invention held over the largest equipment manufacturer on Earth. The invention was called the Power Control Unit. It weighed about 600 pounds. It ran on a single half-inch wire rope, and for 3 decades it controlled every blade, every scraper bowl, and every piece of towed equipment in the construction industry. This documentary covers 4 things. First, we are going to open up the Power Control Unit and explain exactly how it worked, gear by gear, drum by drum, because no video on YouTube has ever done that properly. Second, we will show you what it actually felt like to operate these machines through the words of the men who ran them. Third, we are going to walk through the most important business relationship in construction history, the partnership between LeTourneau and Caterpillar, and how it fell apart. And fourth, we will explain exactly how and why hydraulics killed cable control forever, and why the man who invented cable saw it coming before anyone else. Think of this video like a flight with 4 stops. We are starting inside the machine, then moving to the operator's seat, then to the boardroom, and finishing on the job site where cable made its last stand. We will tell you when we arrive at each one. R.G. LeTourneau held 299 patents over his lifetime and supplied 70% of all Allied earth-moving equipment during World War II. His biography is a story worth its own documentary. But this video is not about him. This is about the machine he built that made everything else possible. Let us start inside the Power Control Unit. The Power Control Unit was an enclosed, gear-driven, multi-drum cable winch that bolted directly to the rear of a crawler tractor. If you have ever seen the back end of a vintage Caterpillar D7 or D8 on a construction site, the Power Control Unit was that heavy cast iron box mounted behind the operator's seat, usually coated in grease and dirt. It did not use a standard power takeoff. Instead, it tapped directly into the tractor's upper transmission shaft through a splined connector that slid into the back of the transmission case. That is a critical distinction. LeTourneau was not borrowing leftover power. He was pulling force directly from the heart of the machine. If you could open up the cast iron housing and look inside, you would see heavy steel gears meshing in oil. A pinion gear on the spline shaft drove an idler gear, which turned 2 main gears, one on the left and one on the right. Each main gear drove its own cable drum. LeTourneau used exclusively stub spur tooth and herringbone gears throughout the entire unit. He completely eliminated bevel gears and worm gears. The reason was simple. Bevel and worm gears generate heat, waste power through friction, and require constant lubrication in dusty conditions. Straight-cut spur gears run cooler, transfer power more efficiently, and tolerate the kind of dirt and grit that covers every piece of equipment on an earth-moving site. The gear ratios were interchangeable. LeTourneau designed what he called a neck, a removable adapter section between the tractor and the PCU housing. A mechanic in a workshop could swap necks to change the drum speed for different jobs. A 7.1-to-1 ratio for fast, light work. An 11-to-1 ratio for standard scraper operation. a 28:1 ratio for slow, heavy pulling, and a 38:1 ratio for the most extreme loads. The operator did not change ratios in the field. The neck was swapped between jobs, sometimes between seasons. The clutch was where LeTourneau's engineering instincts showed most clearly. Picture 2 machined steel cones, one male and one female, with a 15-degree taper angle. The main gear hub was bolted to the driving cone with 12 cap screws, and both rotated together on tapered roller bearings seated on a part called the clutch throw nut. This throw nut was threaded onto the stationary drum shaft. When the operator pulled a steel lever next to his seat, the throw nut rotated on its threads and translated that rotation into axial movement, pushing the cones together to engage the clutch or pulling them apart to release it. Here is a detail that shows how carefully this was thought through. The left-hand and right-hand drum shafts had opposite thread directions, left-hand thread on one side, right hand on the other. This ensured that the same lever motion engaged both clutches in the correct direction, regardless of which drum the operator was controlling. The brake was a self-energizing, spring-applied, split-band brake. A lined brake band wrapped around the outer surface of a heavy steel brake drum. A tension spring pulled the band tight by default. And here is the genius of the design. The harder the load tried to unspool cable, the tighter the brake gripped. This was a fail-safe system. If the operator let go of the lever, if the diesel engine stalled in the middle of a cut, if anything went wrong at all, the brake locked automatically. The load held. The cable stayed put. If you are enjoying this deep dive into the technology behind construction history, like and subscribe so you do not miss our next Before Hydraulics episode. 3 lever positions controlled everything. Push forward to engage the clutch and hoist the cable, winding it tight around the drum. Center position for neutral, where the spring-loaded brake held the load in place. Pull back to release the brake and let cable free spool under gravity. When the operator released the lever at any position, the spring returned it to center automatically. Neutral was the default. Safety was built into the physics. Now let us talk about the cable itself, because this single component is the reason cable control eventually lost. If you pick up a piece of scraper cable and hold it in your hand, it feels like a living thing, stiff but flexible, heavy but precise. The standard wire rope was ½ inch in diameter, about the thickness of a man's index finger. 6 strands of 19 wires each, wrapped tight around an independent wire rope center core. Langley construction meant the wire lay and the strand lay ran in the same direction. This gave better abrasion resistance on sheaves and drums as the cable ran back and forth under load, but it also made the cable more prone to unlaying if a cut end was not properly seized. The material was improved plow steel, not the stronger extra improved grade, because the cable needed some elasticity to absorb the shock loads of a scraper bowl slamming into hard ground. Braking strength was roughly 20,000 pounds, about 10 tons. For a Caterpillar number 60 scraper, the ejection cable measured ½ inch by 75 feet. The bowl lift cable was ½ inch by 60 feet. The apron lift cable was 9/16 of an inch by 18 feet. Each cable dead-ended on its drum through a wedge-shaped pocket. You threaded the steel wire rope through, inserted a tapered wedge, and the load itself locked the wedge tighter. Setting up cable was described by experienced operators as exasperating until you get it down. But once you figured it out, it held. The cable ran from the drum at the back of the Caterpillar tractor through a double-deck sheave assembly, a set of heavy steel pulleys mounted on a frame at the rear. The sheaves were 9 3/4 inches in diameter. specifically sized to prevent premature cable failure from sharp bends. If the pulley was too small, the cable kinked and the wires broke from fatigue within days. If the groove was too shallow, the cable flattened into an egg shape and lost its strength. LeTourneau machined his grooves deep enough to support the cable on both sides, not just the bottom. The upper sheave slowly swung back and forth as cable spooled in, laying it evenly across the drum, like thread on a bobbin. The lower sheave swung freely to maintain alignment with the trailing scraper at whatever angle it happened to be tracking behind the tractor. Bearing adjustment on these pulleys required shim thicknesses of 7/100ths and 14/100ths of an inch. The manual specified that bearings should be slightly preloaded, meaning it took considerable force to turn the drum by hand. Too loose, and the cable would stack unevenly on the drum. Too tight, and the bearings would overheat and seize in the middle of a shift. Every one of these specifications came from LeTourneau's own instruction books, and every one of them represented a lesson learned the hard way. A frozen sheave bearing could saw through a half-inch cable in seconds. An improperly shimmed drum could cause cable stacking that jammed the entire system. The tolerances were tight because the consequences of getting them wrong were measured in broken bones and lost lives. That brings us to our second stop, the operator's seat. Cable scraper operators were a breed apart from everyone else on a construction site. They were called cable men, and they learned their trade not in a classroom, but by watching, by feel, and by breaking things. The levers were mounted horizontally on the front face of the fuel tank, right behind the operator's open-air seat on the Caterpillar crawler tractor. Each lever controlled one drum. Push one direction to hoist, center for hold, and push the opposite direction to free spool. The operator was also managing the tractor's steering clutches with both hands, the throttle, the gear selection, and visually monitoring a scraper bowl dragging through the dirt, 20 or 30 feet behind him. All of this happened while bouncing across rough, unprepared terrain at walking speed in the open air, with no cab, no rollover protection, and nothing between him and the ground but a steel seat bolted to the frame. An experienced cable man on a heavy equipment forum said that the feel and control a cable unit puts back into your hand is something no hydraulic lever can deliver. Another operator said it was an unspoken rule that the care of the cable was up to the man running the machine. If he broke it, he fixed it. He greased the sheaves, fed new string through as needed, and knew every sound that winch made before it made it. The word feel comes up repeatedly in every account from cable operators. They could read the cut by the tension in the lever. They knew when the drum was about to overwind. One man on the ACMOC forum put it perfectly. Every winch had a personality. You did your adjusting with the engine shut down because a stuck clutch would not feel a thing as it wound you through the sheaves. There were iron rules that cable men followed without exception. You never worked on cable with the engine running. If the clutch grabbed while your hands were near the drum, the cable would drag you right onto it. You started the engine on the pony motor with the diesel fuel off, because if the clutch stuck, you could throw out the pony clutch and stop the blade from snapping a line. And you respected the sheaves. If the bearings ran dry, they cracked from heat, and a locked sheave would saw through a cable in seconds. The death toll of cable scrapers in the 1940s was staggering. Roughly 1,800 American operators died on these machines between 1940 and 1955. The cables that built the modern world also killed the men who ran them. But the danger was never in the design of the power control unit itself. The PCU's self-energizing brake was genuinely fail-safe. The danger came from cable fatigue, from neglected maintenance, and from the single fundamental limitation that LeTourneau could never engineer away. Cable can only pull. It cannot push down. There was one design flaw, though, that went beyond cable itself. On the early LS carryall scrapers, the bowl push beam projected forward with sheave blocks positioned directly above the operator's head. Apart from dropping grease and debris on the man below, if the hitch on the tournipull broke, and they often did, the entire push beam would collapse downward onto the operator. LeTourneau redesigned this after 1944, routing the push beam rearward instead. But the early machines earned a reputation that followed cable scrapers for decades. The tournipull itself picked up a nickname that tells you everything about how operators felt. They called it the Widow Maker, not the later electric-steered models, which were comparatively civilized. The early clutch and brake steered versions were the dangerous ones. It was dangerously easy to jackknife a C tournipull going downgrade. The operator had to cross steer using the opposite clutch going downhill, and a moment of inattention by a novice could flip the machine or send it careening off a fill slope. Experienced operators treated these machines with the kind of respect you reserve for something that can kill you before you realize what went wrong. On a double-acting hydraulic system, a double-acting cylinder applies force in both directions. It can lift a blade and press it into the earth with thousands of pounds of downforce. A cable system relies entirely on the weight of the implement itself. If the ground is hard, the blade bounces. If the ground is rocky, the scraper skips. There is no way to force the cutting edge deeper except by adding dead weight, which makes everything heavier, slower, and harder to control. That single limitation is the thread that runs through everything we are about to cover. Keep it in mind as we move to our third stop, the boardroom. In 1934, R.G. LeTourneau signed a co-prosperity agreement with Caterpillar. Under this deal, LeTourneau became Caterpillar's official implement manufacturer. The following year, Caterpillar persuaded LeTourneau to move his manufacturing operations from Stockton, California, to Peoria, Illinois. LeTourneau built a new factory on 23 acres along the Illinois River, close enough to the Caterpillar plant that finished tractors could be shuttled between the two facilities by rail. The arrangement worked like a factory assembly line split across two buildings. When a Caterpillar crawler tractor was finished at the East Peoria plant, workers loaded it onto a railcar. That railcar traveled a short distance down the track to LeTourneau's factory. LeTourneau's crew installed the power control unit, the blade, the scraper hitch, and whatever the order called for. The completed machine then shipped to the customer through Caterpillar's dealer network as a single package. Like and subscribe if you want to see more of the untold stories behind the equipment that built the modern world. This arrangement made both companies dependent on each other in ways that neither fully controlled. LeTourneau needed Caterpillar's dealer network and brand recognition. Caterpillar needed LeTourneau's attachments because they did not make their own. At the peak of this relationship, just about every track-type tractor coming out of the East Peoria plant was equipped with LeTourneau hardware. That is not an exaggeration. A retired Caterpillar employee with 37 years at the company confirmed it directly. But in 1937, something happened that cracked the foundation. LeTourneau was recovering from a serious car accident when he conceived the idea for a self-propelled motor scraper. Instead of a crawler tractor pulling a separate scraper, he wanted to build a single machine where the engine and the scraper were one unit. He brought the idea to Caterpillar management and asked them to build and market it. Caterpillar told him the concept was not feasible, so LeTourneau built it himself. The Model A tournipull entered production in 1938, and its first real test came at a project that most construction history videos have never mentioned. In late 1938, the Guy F. Atkinson Company ordered 10 Model A tournipulls for the Hansen Dam project in the San Fernando Valley north of Los Angeles. A catastrophic flood had swept through the Los Angeles basin in February and March of 1938, sending walls of muddy water through neighborhoods and farmland, killing 115 people and causing $78 million in damage across Southern California. The Army Corps of Engineers responded with an emergency flood control dam program, and Hansen Dam became the centerpiece. The dam was enormous. It was 9,050 feet long, nearly 2 miles, making it the largest earth-fill dam of its type in the world at the time of construction. It stood 97 feet above the streambed and 700 feet wide at the base. Over 13 million cubic yards of earth were moved, and the machines that moved most of it were LeTourneau tornapools, every one of them cable-controlled through power control units. Hansen Dam was the first major earth-moving project in history done primarily by motor scrapers, not by crawler tractors pulling separate implements. It used self-propelled machines that could load, haul at 15 miles per hour, dump, and return at 25 miles per hour. The construction took roughly 1 year, from September 1939 to September 1940. Nearly 1,000 men worked the site. The general contractor, Guy F. Atkinson Company, out of San Francisco, was one of LeTourneau's most loyal customers. Atkinson had used LeTourneau equipment at Bonneville Dam and would go on to use it at Grand Coulee. George Atkinson, the founder's son, later personally presented LeTourneau with an industry award in 1958. What made Hansen Dam significant was not just the scale. It was the proof of concept. Every tornapool on that site was cable-controlled through a power control unit. Every bowl lift, every apron drop, every load cycle ran on the same half-inch wire rope we described earlier, and the machines performed. They outpaced crawler-scraper combinations by a factor of 2 or more in haul speed. The tornapool did not just threaten Caterpillar's business model. It proved that the future of earth-moving did not need a crawler tractor at all. Caterpillar responded by developing the DW10 as a direct competitor. But the real crisis came during World War II. LeTourneau's factories produced roughly 70% of all Allied earth-moving equipment: 14,000 bulldozers, 10,000 carryall scrapers, 1,800 tornapools, 1,600 sheep's-foot rollers. 78 of his inventions were used during the conflict. His plants won the Army-Navy E Award 9 times between them. The scale of cable-controlled equipment in the war is difficult to grasp. Each Navy construction battalion, the Seabees, was equipped with 4 units of 8 to 10 cubic yard carryalls and 4 units of 12 to 15 cubic yard carryalls, all cable-controlled. These units built 111 major airstrips, 441 piers, and over 2,500 ammunition magazines across the Pacific. At Espiritu Santo in the New Hebrides, Seabees carved a 6,000-foot airstrip out of virgin jungle in 20 days, using LeTourneau cable scrapers and bulldozer blades. General Eisenhower listed the bulldozer among the 4 most vital pieces of equipment for success in North Africa and Europe. Admiral Halsey ranked it 4th, right after submarines, radar, and aircraft, among the weapons that won the Pacific War. Every one of those bulldozers ran on cable. Every blade was raised and lowered by a power control unit bolted to the back of a Caterpillar tractor. Anyone who has seen a steel cable snap under tension on a construction site knows what that kind of force can do to a human body. At Hoover Dam alone, at least 13 workers were killed by the cableway system. In the military, that same cable technology was building the infrastructure of victory. One of the most remarkable machines LeTourneau built during the war was something almost nobody knows about: the D4 airborne tornapool. Only 567 were ever manufactured. It was a miniature cable-controlled scraper system designed to fit inside a Waco CG-4A military glider or a C-47 transport aircraft. Army airborne aviation engineers used them to build and expand landing strips immediately after parachute or glider insertions behind enemy lines. The power came from a 44 horsepower Continental flathead 4-cylinder engine. The The cable PCU was a Model P. The scraper was a Model Q carryall with a 2 cubic yard capacity. A surviving example sits today at the National Construction Equipment Museum in Bowling Green, Ohio. A cable-controlled scraper designed to fly. Now we have covered the partnership and the war. Our fourth and final stop is the job site where cable made its last stand. But first, we need to understand the breakup. In 1944, the Co-Prosperity Agreement expired, and Caterpillar chose not to renew it. The LeTourneau was the breaking point. Caterpillar saw LeTourneau's self-propelled scraper as a direct threat to their crawler tractor business, and they were right. But during the war, they could not act. The War Production Board had ruled that Caterpillar should keep building tractors and leave the attachments to LeTourneau. The government literally forced the partnership to continue. The moment the war ended, Caterpillar moved fast. In 1945, they introduced their own cable-controlled bulldozer blades. In 1946, their first pull scrapers. In 1947, their first hydraulic blades. Like and subscribe to follow the entire Before Hydraulics series as we document the forgotten technology that built the modern world. That 1947 date matters enormously. It was not the first time someone had tried hydraulics on a scraper. 12 years earlier, in 1935, the Austin Western Company had built the first all-hydraulically operated scraper in history, a 12-yard model with its own engine and pump. And it flopped. Customers described the hydraulics as expensive to maintain, slow-acting, and leaky. The seals could not handle dust and dirt. The pumps wore out. For the next decade, cable control remained the only reliable option. The transition was not clean. For years, machines existed that used both technologies at once. The Euclid S7 motor scraper from 1954 had hydraulic controls for the bowl and ejector, but still used a cable-operated, gravity-closed apron. Euclid did not go fully hydraulic on the apron until 1963. Caterpillar's DW10 tractor, which was in production from 1938 to 1955, could be ordered with either a lay plant chote hydraulic scraper or a LeTourneau cable-controlled DLS scraper. Exact same tractor, customer's choice. That tells you everything about how uncertain the industry was about which technology would win. The economics favored cable for longer than most people realize. Cable operators on heavy equipment forums still argue today that the latest power control units before they were phased out were absolutely reliable and cost little to maintain. Half-inch scraper cable was cheap. There were no hoses to blow, no pumps to wear out, no hydraulic fluid to contaminate. If you parked a cable scraper for months or even years, you could come back and the system would work. Leave a hydraulic machine sitting and the cylinder seals dry out, the rams rust, and the fluid breaks down. But these advantages only mattered as long as hydraulic sealing technology remained primitive. And by the early 1960s, it was not primitive anymore. But here is where the story takes its strangest turn. In 1945, the same year the war ended, LeTourneau filed a patent that he never publicly discussed. Patent number 2,495,463. It described a fluid pressure actuated disc clutch built inside a cable control unit. LeTourneau had quietly put a hydraulic mechanism inside his own invention. The man who spent his entire career avoiding hydraulic implement control had used hydraulics to improve the internal function of his cable system. He knew that mechanical cone clutches had limitations. He knew that hydraulic actuation was faster, smoother, and more precise for engaging and disengaging the drums. But he refused to extend that logic to the implements themselves. And the reason was not stubbornness. It was strategy. In 1953, LeTourneau sold his entire earth-moving equipment line to Westinghouse Air Brake Company for $31 million. The deal included his plants in Peoria and Toccoa, Georgia, all machinery, inventory, and the current product line. It came with a 5-year non-compete clause. But LeTourneau kept one thing: the rights to his electric wheel technology. And that tells you exactly where his mind was. LeTourneau had started his career in the early 1920s using electric motors to control scraper functions. A generator on the tractor powered electric motors on the scraper. It worked, but the motors were too slow. So he invented cable control as a faster alternative in 1928. After the war, when hydraulics began improving, LeTourneau did not switch to hydraulics. He went back to electric. He skipped an entire generation of technology. By 1958, every new LeTourneau machine used diesel-electric drive with electric wheel motors built directly into the wheel hubs. His reasoning was consistent throughout his life. He wanted to eliminate unnecessary parts. Cable was simple. Electric was controllable. Hydraulics, in his view, were messy, leak-prone, and added complexity that a well-designed cable or electric system did not need. The market disagreed. Through the late 1950s and into the 60s, hydraulic sealing technology finally matured. High-pressure systems became reliable. Double-acting cylinders gave operators what cable never could: downforce. Push and pull in the same cylinder. The ability to press a blade into hard ground with thousands of pounds of controlled force. One of the last machines to fight this transition was the LeTourneau Westinghouse C500 Tournepool, a massive motor scraper that entered production around 1960. Twin General Motors 8 V71 diesel engines, producing 275 horsepower each, mounted in a cab-over configuration. Twin-disc power-shift transmission. 30 miles per hour top speed on a highway. 16 to 21 cubic yard capacity. Electric motors attached to short lengths of steel cable for bowl and apron control. Electrically driven rack and pinion ejector. And here is the part that sounds like science fiction for the era. No steering wheel at all. The operator sat in the cab and controlled everything with electric toggle switches. The C500 was arguably the most technologically advanced motor scraper of its era, but only about 70 units were ever manufactured before production ended in 1964. The reason for its failure was stated bluntly by the historians who documented it. The scraper was still an all-cable-controlled machine when the industry had already embraced hydraulics. By the mid-1970s, even Caterpillar, one of the last companies still manufacturing the power control unit line, had discontinued its entire production. The technology that had built Hoover Dam access roads, the Hansen Dam, the Alaska Highway, every Allied airfield in the Pacific, and the interstate highway system was gone. The cable men disappeared with it. The old-timers are gone now, as one forum member put it. And he added something that stuck with us. Sad thing is, most all of the old-timers are gone. The skills those men carried in their hands, the ability to read a cut by the tension in a lever, the instinct for when a drum was about to overwind, the daily ritual of greasing sheaves and feeding new string. All of it vanished within a single generation. In the United Kingdom, some operators held on longer than anyone else, running cable scrapers well into the 2000s. Komatsu was reportedly the last manufacturer still making double-drum power control units. But eventually, every one of those machines was either scrapped, converted to hydraulic operation, or parked in a museum. But the story has one more turn that most people miss. LeTourneau's trajectory across 50 years of engineering was not a straight line from cable to defeat. It was a circle. He started with electric in the early 20s. He switched to cable in 1928 because electric was too slow. He perfected cable through the 30s, 40s, and 50s. And then he went back to electric, skipping hydraulics entirely. His last machines used diesel-electric drive with motors built into the wheels. Modern mining trucks, The 360-ton haul trucks working copper and iron ore mines around the world today use diesel-electric drive, the same principle LeTourneau championed. The industry laughed at him for refusing hydraulics in the 1950s. 60 years later, his electric wheel concept powers the largest vehicles ever built. This pattern has played out before in construction history. When Caterpillar introduced the diesel engine in 1931, steam did not just disappear. The old technology planted a seed inside the thing that replaced it. Steam gave way to diesel. Cable gave way to hydraulics. But the electric drive that LeTourneau abandoned in 1928 came back and conquered the biggest machines on Earth. The power control unit is gone, but the man who invented it was right about where construction was heading. He was just 60 years too early. Deadly steel cables at Hoover Dam and the full story of R.G. LeTourneau's 299 patents are both available on this channel. Like and subscribe so you do not miss a single episode. We will see you in the next one.